As far as memory chips are concerned, so they can be classified into two major classes. One is the ROM, that is read only memory, another is RAM, which is random access memory. So, the memory chips that we are talking about, so there are two types, one is ROM, another is RAM. So, these we know from our digital logic classes. Now, as far as the controlling these ROM and RAM chips are concerned from the microprocessor or any other CPU. So, these chips they normally have a number of standard lines, so that they are used for interfacing. So, first one is the address lines. So, these are the address pins. Now, so there will be a number of lines, like if this ROM or this memory is having say m, it is m cross n memory, that is there are m locations in the memory and each location is of n bit wide. Each location is n bit wide and there are m such memory locations. Then this address line, so there I will need log m to the base 2, so many number of ceiling of that. So, so many number of lines which will serve as the address line to select individual locations of the chip. So, this is an input to the memory chip. So, similarly, I will have the output which is given by the data. So, this is often known as address bus and this data part is known as the data bus. So, this is having n number of lines. Okay. So, since each location has got n bits, so I need n locations to identify to get the data of those n bits values. Now, apart from that, there are some other controls which are also there that can help us in connecting memory chips to the processor. One of the important lines that we have is known as the chip select line. So, this is the chip select line. So, if this chip select line is disabled, then this memory does not put any output onto the data bus. The memory content will be available on the data bus only when the chip select line is enabled, and this may be active high or active low. So, this may be active high or active low. So, the connection that we have shown here is for active high connection. If you have a bubble here, so that will mean that it is a active low connection. So, when the chip select line is 0, then the chip is enabled, otherwise it is disabled. And also depending upon the type of operation that we want to do on this chip, so on this memory, so we will have two more control lines. One is called the read and the other is called write. So, they are generally written as read is represented as RD and write is represented as WR. And in most of the cases, this read and write controls, so they are active low. So, there are bubbles here. So, we get the lines as read bar and write bar. So, these are the lines. Now, you can find some chips that has got that have got more than one chip select line. So, so what can happen is that, so this may be chip select 1 or CS1, there may be some another chip select line which is called CS2. Okay. And the logic is that for the chip to operate, both CS1 and CS2 be enabled, so to get the output, and this helps in the decoding process. When we are connecting this chip to processor to ensure that we select the proper chip, so the decoder has to be there, as we have seen in the last class. So, the decoder design will be simple if we have got multiple chip select lines. Now, depending upon the type of memory, so this read bar and write bar lines will come. For example, for a ROM, there is no option to write the content onto the ROM. So, this write bar line will not be there for ROM. So, for RAM, I will have both read bar and write bar lines. For ROM, we will have only read bar line. So, let us take an example and try to see how this can be utilized in connecting some memory chips to a processor. We take an example where I need to connect 8 kilobyte of ROM and 16 kilobyte of RAM to a system with a CPU that has got 16 bit address bus, 16 bit address bus. Now, 16 bit address bus means the addresses can go from 0 to 64K. So, I can connect 64K space memory to the processor. Now, this ROM and RAM, so it is required that this ROM will be starting at location 0000 hex, whereas this RAM it should start at location 8000 hex. So, this will help us in distinguishing the RAM space and ROM space. So, that is useful in many cases. So, we do not want that maybe for the future extension we would like to put more ROMs into the system. So, that if I keep some gap between ROM and RAM connected to the system, their addresses, then I will be able to extend the ROM space later. So, this may be the requirement. So, accordingly we can design a system where this connection will be there like that, and it is given that the memory chips, that is the both these ROM and RAM chips. So, they are of size say 4 kilobyte. So, each of them is 4 kilobyte. So, to make an 8 kilobyte ROM, so you need 2 such ROM chips. For making a 16 kilobyte RAM, we need 4 such RAM chips. So, how this system will look like? Okay. So, if we want to get a representation, so suppose first 2 chips that I put, so they are the ROM chips. So, these are the 2 ROM chips that I have put. So, we call it say ROM 1 and ROM 2. We call them ROM 1 and ROM 2. Now, after that, this is ROM 1, this is ROM 2 like that, and then I will have so that will so each ROM is 4 kilobyte. So, that makes 8 kilobyte. Then this 16 kilobyte of RAM, so that can be made by putting 4 such RAM chips. So, these are 4 such RAM chips which makes it 16 kilobyte of RAM space. So, they are all RAMs, RAM 1, 2, 3 and 4. Now, this side I have the processor, this side I have that CPU, from where I have got that address bus and data bus lines going out. So, since each chip is 4 kilobyte, so to address 4 kilobyte I will need 12 bits of address, 12 bit of address lines will be sufficient to differentiate between the locations of individual chips. So, from the address bus what I do, I take the lines A0 to A11. So, that is the 12 bit lines, and that goes to the address line of individual chips. So, they go to the address line of individual chips. This part is done, and similarly the data bus that we have. So, data bus will connect to all the chips. So, the data bus is 8 bit. So, data bus connects to all the chips. Okay. So, this is bidirectional, this data bus is bidirectional and the address bus is unidirectional. So, that is done here. Address bus is like this. Now, so this is the basic connection. Now, I have to select the chips. Okay. So, for the chip selection what we do, that see, you look into the difference in the address, that the ROM starts at 0000. So, with the most significant bit. So, this is a 16 bit number, the most significant bit there is 0, and here this most significant bit first digit is most significant digit here will be 1, because the 8 will be represented as 1000 followed by 4 zeros. So, this way that 16 bit number will go, and the most significant digit there is 1. So, we use that to differentiate between the ROM space and the RAM space. Okay. So, for differentiating between these two ROMs, what we do? We put this type of gate. So, where this the line A15 and A12. So, they are connected here. So, A12 and A15, the lines being 0, will say that this will connect to the chip select of this ROM chip. Okay, so, this is the chip select of this ROM chip. Similarly, the second ROM chip will be selected provided this A15 line is 0, A15 line is 0, but A12 is 1. In that case, this chip select will be generated and it will be connected to the second ROM chip. So, this is the chip select of the second ROM. Now, for the remaining RAM chips, so what we can do? We can put a decoder, a 2 to 4 decoder, and in that 2 to 4 decoder we take the lines A12 and A13. So, this is my line A12 and this is the line A13. So, they are coming here and accordingly this will generate 4 outputs, and these 4 outputs I can connect to RAM, but I need that the line, the bit A15, that should also be 1. For making the line A15 to be equal to 1, what I need to do is I need to connect it in this fashion. So, this should go to the chip select of RAM 1. Similarly, the second one can be connected like this. This A15 line, this is ANDed with this output of the decoder and it is going to the chip select of the second RAM chip. Similarly, this line A15 ANDed with the third output of the decoder, that goes to the chip select line of the third chip, and this A15 line ANDed with the fourth output of the decoder. So, this will go to the chip select of the fourth RAM chip. So, this way now you see that so this is a 2 to 4 decoder, this is a 2 to 4 decoder. So, that decoder, so now you see that we can, this RAM has been put into the address space 8000 onwards and the ROM has been put into the address space 0 onwards. Now, I said that so what is the address range for the first ROM? So, for ROM 1, the address range is basically 0000 to 1FFF. So, this is the address range for the first ROM. For second ROM, so this is 20 for ROM 2. So, it is 2000 to, this is 2000 to 2FFF. So, this is the address range for the second ROM. And of course, since you see there will be folding, because I have not used the line A13 and A14 while decoding this ROM chips. So, they will get folded. As a result, I will also have I will also get this. So, this actually this ROM chip. So, this is 1FFF. So, this is your 12 plus 1 13 bit. So, 13 bit means 2 power 13. So, it is basically 8 kilobyte. So, so this is this 1FFF. So, this is the complete ROM space. So, this is the complete ROM space that we have, and out of that, so this is wrong. So, this is the complete ROM space. Out of that, the first this is total of 8 kilobyte. This is total of 8K here. Out of that, first 4K locations will belong to ROM 1 and the second 4K location they will belong to ROM 2. Now, there will be folding, as I was telling. So, for if you again come to the next address space, like what happens is the lines A13 and A14, they are taken as 00. They are taken, they have not taken in this diagram. So, in this particular case, what is happening is that A13 A14 is remaining as 00. Now, if A13 A14 gets a value 0 1, then what you are getting is the address range 2000 to 2FFF. So, this is the next address space that we are getting. So, this is basically a folded address space of the first ROM, for the first address space that we have got. So, these two address spaces are same, they map to the same set of memory locations, okay, but because of folding they are coming. And similarly, the two bits A13, A14, so they may be 1 0, and as a result you will again get the same address space repeated from 4000 to 5FFF, and when the bit 2 bits become 1 1. So, you get the space repeated from 6000 to 7FFF. How are you getting this 2, 4, 6 these numbers? So, if I just write the bit numbers 15, 14, 13, 12, the last 4 bits of this address space. Now, for the RAM selection, this bit is always 0. So, out of that, so this bit number up to bit number 12, so these are they have been utilized in the ROM selection. Now, if these two bits are 0 0, now this can go to so this can so now this bit can remaining bits A0 to A12, it can vary from all 0 to all 1. So, that way we get the first address space which is 0000, it can go up to the situation where these bits remain 0, but this is 1. Okay. So, that way when this bit is when this A12 bit is 0, it is scattered by the first ROM, when this A12 bit is 1, it is scattered by the second ROM. So, that way it is generating this whole address space. So, 0. So, this first 0 that we have here is corresponding to this 4 bit 4 zeros here, and this first one that we have here. So, that corresponds to this one here. And now, if we are going for the next setting of A13, A14. So, this is 0 1. So, this bit is 0. So, this is 0. So, this value is basically 2. So, you see that this next address space starts at 2000 and go up to and goes up to 2FFFF, where these bits are 0 0 1, and then it can go up to this all these values, it can go up to all ones values. So, that way it can go up to this 2FFF configuration. So, this way this ROM chip and RAM chip, they can be connected. Now, if you are looking into the RAM space, if you are looking into the RAM space that we have connected here, then this RAM, it will have the address range 8000 to it will have the address range 8000 to BFFF as the first address space, and there will be another folded address space, which is C000 to FFFF. So, this will be the folded address space. Okay. So, there is a folding here, and this is again guided by it is again guided by this selection, like A15 has been used, A12, A13 has been, but only the A14 line is not being used. So, if you just put values of A14 to be 0 or 1, so when A14 value is 0, you get the first address range, and when A14 value is 1, get the second address range. So, this value will come when A14 is equal to 0, and this address range will come when A14 is equal to 1. So, this way you can interface ROM and RAM chips to a system for getting the whole design memory, getting the memory map as you desire for your system. Next, we will look into another important topic that we have that will need for this microcontroller course, which is the concept of the registers. So, in the last class, I have introduced the concept of registers, and I said that a register, it is a sequential element and it stores the values of some bits, okay, and these values can be stored in different ways, you know. So, I can have this, if this is a register and I say that this is say a 4 bit register. So, it can store a 4 bit value. Now, the requirement is that these 4 bits, the 4 bits that we are talking about, So, these 4 bits may be loaded parallelly, or so if this is a 4 bit register, then these 4 bits may be loaded parallelly, or these 4 bits may be loaded serially 1 bit at a time. Okay. So, one is the parallel load, and other combination that I can have is a serial load, both are possible. Similarly, I can so it may so happen that I have got a number of such registers. Instead of having a single register, I have got a number of such registers. Now, I need their output to come onto a common line, which we call a bus. So, their outputs are connected to the bus. Now, at any point of time, I may want that output of only one register be available and others are not. Okay. So, for that purpose, what I need is these registers, they should have another control, which is output enable, and when this output enable signal is given, then only the output of the register be available onto the bus. So, this is the bus. Similarly, this has got separate output enable line, this also has got a separate output enable line, and this output enable lines, so they whenever the control is given, then only the output should be available on the bus, otherwise not. Similarly, when I am feeding input to this register, so instead of feeding them differently, I can feed them from a single 4 bit bus. I can feed them from a single 4 bit bus, and there can be a separate signal which we call load. So, there can be a load signal, and using this load signal, the values should be loaded into the register. So, if I put a value onto this input bus and give load signal to the first register, then the value should be loaded into the first register. If I give load signal to the second register, then the value should be loaded in the second register. So, that sort of facility is needed. So, we can very easily design such a circuit where these individual stages, individual registers, they can have load and output enable control lines. So, ultimately I have a register will be something like this. If this is a say 4 bit register, if it is a 4 bit register, then I should have the facility to parallelly load the line. So, this is 4 bit parallel data, parallel input, or I can have 1 bit serial input. I can have 1 bit serial input. I can have a 4 bit parallel output. I can have 4 bit parallel output. So, this is 4 bit, or I can have a single bit serial output. So, this is a serial output, can have single bit serial output. And apart from that, I should have control, like whether I want a parallel load. So, this load signal, so this normally stands for parallel, or for the serial load. So, the control signal is generally called shift. This is the serial load. It is called shift because when you are if this is a register and it has got 4 stages, then when you are loading the next value serially here, the previous value that was stored here gets shifted to the next position, the value that was here gets shifted in the next position, this goes to the next, and this value, the final value gets lost, or it is available at the serial output. So, this is known as the shift output, shift control or serial control. So, these are the control lines that I should have in the register. Now, how to design such a thing, such a system? So, that we will see. So, as these individual stages of the flip flop, individual stages of the register, so it consists of a D type flip flop. So, we have got D and Q lines there. Now, what I want is, if the shifting is there, then I should give the serial value and that should be shifted in. So, one input for the D can come from this serial input and the shift control. The other possibility is that I am loading it parallelly. So, when I am loading it parallelly, then I should have this parallel in and the load control, and depending upon whichever control is given. So, I can have an OR gate, they can connect to this D flip flop, and for the output part I can have two output, parallel output and serial output. So, for that matter, so I can have one AND gate here where this value is coming and the other value that is there is a read. So, if I give the read signal, so this is the parallel output, and if I give a shift signal, then this will be the serial output. This is the serial output. So, this is what we are looking for, plus the clock signal will be there, everything is synchronized with a clock. So, the clock signal will be there. Now, you can if you are connecting two stages, say I am just showing two stage of that register, though there can be 4 such stages. So, I am just showing 2 stages. Now, this parallel input line, so though it is so there are 4 lines. So, out of that the first 2 lines I am showing, there are 2 more lines which will be connected to the next stages that are not shown here. So, this is the 4-bit parallel input. Out of that the first bit is connected to the first flip flop, second bit is connected to the second flip flop, like that. But serial in, so the first bit is connected directly. So, this is the serial in, and this serial output of this flip flop should be connected to the serial in of the next flip flop. So, this is the serial output of the first flip flop connected to the serial in of the next flip flop. Then the I will need the parallel output line as well. So, this parallel output lines will be taken from these individual flip flops and they will be taken into, they will form this 4-bit output coming from the successive stages. They will make the 4-bit output, parallel output, and this serial output for the last flip flop that we have, whatever be the shift out. So, that will be the, this serial output will be the shift output, this will be the shift output. Now, other controls like this load control, then this shift control, they should be given to all the stages. The load control and the shift control, they should be given to all the stages for doing the operation. Okay. Clock signal should be given to all the stages. This is the clock signal. The clock should go to all the stages. Then this structure will behave as a register where you can parallelly load the value or you can serially load the value. You can take a parallel output, you can take a serial output. Okay. So, all those operations are needed when we are incorporating these registers inside microprocessors.